So, what is object-oriented programming? Well, it was invented in the 1960s for a language called Simulus 67, and then it was later picked up and used a little more widely in a language called Smalltalk. The simplest way to talk about object-oriented programming is as a paradigm or as a way of organizing our code. As you've probably realized, all programs are comprised of code that's designed to process data. We store the data temporarily in variables, and then we call functions to process the variables. The object-oriented paradigm organizes the data into specially designed entities called objects, and the functionality for processing the data into specialized functions that we call methods. The design of these objects and methods is specified in a kind of a blueprint, which we call a class. This paradigm is one of the most important advances in software design. It promotes collaboration and the extension and maintenance of our code. And because its ability to help us manage complexity is so profound, it is the primary paradigm used for software design. It's hard to overstate just how important it is to programmers every day. And it's simple enough to begin implementing that it can make your coding work easier every day, too. Now, as a way of explaining the difference between object-oriented code and non-object-oriented code, let's look at a really simple example. The code on the left is what we call procedural code, and that's the word they use when they mean non-object-oriented. As you can see, we're taking an integer and passing it to a function called increment, and then catching the result in the same variable name. And in the end, we print the integer, and you can see it's been incremented twice. Compare this code to the code on the right. This is not an integer in the object paradigm. This is a myCustomInt object. It's an object that I designed myself in a class called myCustomInt. The myCustomInt design includes a method called increment, and I'm calling increment on the object. Now the result is the same, and you can imagine that within the myCustomInt object, there's an integer there. But again, it's not an integer. It's been designed specifically to my specification, and I've included a special method to work with it. It doesn't illustrate exactly why we need objects, but it does show the difference. In the procedural paradigm, we might design a function that works with an integer, and it would be doing the same work as the object. The difference is, in the object paradigm, we actually have a custom type of object that has its own special method for doing this incrementing. The functionality and the data are connected, and that's really the best way to begin thinking about objects. Data plus functionality. Now, just to satisfy your curiosity, here's the code behind both of those examples in the previous slide. The code on the left should be self-explanatory, but I won't go into what's going on the right here because that's going to be the topic of some upcoming lessons. Now, it's going to take several lessons, really, for it to become clear to you exactly why we need object-oriented programming. The short answer is that it just makes our lives easier. And when we have very complex programs, objects make it so much easier to handle the complexity, also to work with other developers on the same code, and to communicate exactly what the library does to people who might use it. For this reason, object-oriented programming is a universal paradigm used in many languages. And it's safe to say that learning object-oriented programming is a necessary next step into the larger world of software engineering. Now, a full description of objects wouldn't be complete without talking about the three pillars. We're going to discuss each of these in upcoming lessons. For now, I'll just let you know what they are. I also might mention that I had this as a question in an interview many years ago. What are the three pillars of object-oriented programming? I wouldn't be surprised if they're still using this question. The answer is encapsulation, inheritance, and polymorphism. Those may not mean very much right now, but we'll be discussing them much more extensively going forward.